Okay.
Good afternoon, or good morning, or good evening, whichever time you're listening to this. This is a 2-hour lecture beginning heat transfer, second session, chemical engineering 320, and mechanical engineering course as well. What course is that? Let's go to up here to courses, and mechanical engineering course is 343, mechanical engineering course. Anyway, going back, let's go over the course briefly to see what we're going to be covering this time. I guess we could go right in here, sorry. Bring up the course material. Okay, and you quickly see a number of items in here. You have the syllabus for the course, which we'll come back to. We'll have heat exchanger notes involved here. You obviously have a series of old exams. One of the best ways of studying a course is looking at old exams. Mills book, excuse me, we're not going to be using. And this insulation discussion was included just be of interest to you. But anyway, let's take a look and see what we have in the syllabus area. And go over exactly what I expect. This would be for the ME and 320. Basically, this is summer 216, whereas the other one, Chemical Engineering 320, outlined basically as summer 17, I think. Anyway, we're going to talk about the fundamentals of heat transfer, which involves conduction, convection, radiation. It involves boiling and condensation, and also discusses heat exchangers. You have a number of prerequisites here. Heat transfer, practical approach by Singal, 2007. You can use any edition, 3, 4, or 5, whatever. You can use even Mills's book if you can get by with it. I'm not particularly particular about the textbook. Your whole goal is you want to do well in the exams. There's 2 exams, 2 tests. Usually the first 2 weeks test, second 2 weeks a test, and then there's a final exam, which is 100 points. So total-wise, there is 300 points to this course. Grading, well, homework. Homework's a very good thing. You should always do your homework. Unfortunately, my experience is a large portion of classes copy homework. So homework becomes not nearly as important. The old exams are extremely important because it lets you get an idea of what I expect. Total grading, 300 points. I put in 60, 70, 80, 90%, but this is just for boilerplate. Expectations, you are expected to spend 36 hours a week on this course. This is almost a full-time job, this one single course. So I expect performance out of you, all right? Warning, if you need a C or better in chemical engineering, I suspect that's also true. Basically, looking at the different subjects, we are going to be doing heat exchanger handouts first 4 or 5 days. And we'll go into convection chapters, maybe. And then maybe we'll go into boiling and condensation. Actually, not maybe. We'll probably go into convection first, boiling and condensation, conduction, radiation, and then final exam. You can see that I have here the test is in this, I said the second week, and the test is probably also in the 4th week. It's one back from these. So we start the course. Homework, if not assigned, well, you want at least 5 problems in the first 70 problems in the book. Take 15, 25, 35, 45, and 55 would be excellent. But the whole thing is heat exchangers, convection, conduction, boiling, condensation, radiation, and then we're done. Okay? So that takes care of the syllabus. You understand how you're going to be graded, 2 tests and a final. These are all the learning objectives, right? And so that takes care of that. So we'll close that up and see where we wind up. I guess we did not wind up back at, oh yeah, we did, right here. So again, the old exams are kind of mixed up because in the third exam will be the heat exchangers. The second exam probably will include some convection. The first exam may consider some convection. What you do is, a smart thing to do would be print all these out, divide them up into convection problems, conduction problems, radiation problems, boiling and condensation problems, and then heat exchangers. Okay. That way you'll see I've reversed the order in the course somewhat, just for adding some sort of variety and spice. So without further ado, let's go up here and hit the first set of notes for this course. And first thing you recognize is your textbook is not very good in heat exchangers. What can I say? So there's 2 excellent books, Working with Heat Exchangers by Gupta. This is basically a paperback. Excellent book, especially for young kids like yourself. Okay. And then there's this really fairly sophisticated book by Stanley Yodel, Working with Shell and Tube Heat Exchangers. This book is to give you basic fundamental knowledge, and this is so you can walk in like a real stud, I'll tell you. Yeah. This book does 2 things. It teaches you about shell and tube heat exchangers in depth and puts you to sleep at night while you're reading it. It's a good, 10 pages a night here would be a real challenge for you. Of course, if you were reading these books 10 pages a night, take a look at that. This is about 600-page book, so in 60 days you would have had that read, and this is probably a 300-page, 400-page book, so it would be 40 days. So, that's when you get to be a professional, not one of these college students. This is when you're a pro. 2 other books I admire. One is Process Heat Transfer by Kern, and another one is Basic Heat Transfer by Ozisic. This book was a very excellent book as well. So I like all 4 of them books. Besides the book you have, I can't help that. So basically, let's take a look. We'll just run through some of these things. Heat flows from hot temperature to low temperature. Remember, fluid flows from high pressure to low pressure. Heat flows from high temperature to low temperature. You can't measure heat. You can measure temperature and changes in temperature, but you can't measure heat. They don't quite have a heat meter yet. And if I take a look up here, I have 3 modes of heat transfer: conduction, convection, and radiation. Actually, there's other modes of heat transfer, mixing, basically direct contact heat transfer, where you take, say, a cold stream, a hot stream, mix them together. Boiling, phase change, it's not listed here. Condensation, boiling are not listed here. So there's other modes of heat transfer besides those. Conduction, a little blurb about conduction, which we will get to later, but it'd be, for your own information. Convection, there's you go. You got forced convection, free convection. You got your little equation here. Basically, it's flux, which is heat flow. Q is going to be heat flow divided by area, and all we got is wall temperature here and fluid temperature. So we got the heat flux, and we throw in this heat transfer coefficient. Heat transfer coefficient, and that's what we're often seeking in convective heat transfer. Radiation, electromagnetic waves, and you have the fundamental equation for that, which would be, say, temperature 1. One surface is at temperature 1, the other temperature 2. You have 4th power. You have the Stefan-Boltzmann constant. You have U factor, which is the F times the A. And then you have the emissivity there. Right. Motor phase considerations, like I said, boiling, condensation, very important in heat transfer. And I'm sure if you go into more stranger environments, and you'll run into other things, other types of modes. But for our life on the life on the Earth, we probably have those three main ones plus boiling and phase change. Anyway, let's take a look at the famous pipe wall and heat exchangers. By the way, that's what we're after. This whole area is discussing heat exchangers here. Okay, so I'm sorry. Let's see if we can do a rotation on this thing. That doesn't give it to me. That probably, what's over here? Rotate clockwise. Da, da, da. There you go. So if I take a pipe, okay, I have the temperature of the fluid sitting up here, and I have the temperature outside somewhere. And what happens is I have a convective heat transfer from the temperature of the fluid to the wall. So I have convective heat transfer coefficient inside wall, area of the inside wall, fluid temperature minus temperature of the wall, Ti. Then you have conduction across the tube. I know we didn't discuss conduction, but that's all right. You can grab a hold of it. We're teaching it somewhat differently here. Then we have temperature inside is the Ti, temperature the outside is To at the wall. So you have the temperature difference over which the heat conduction is occurring. And then we have the ln of Ro over Ri divided by thermal conductivity and length. So that takes care of that. And then get the heat from the pipe wall to the outside. We have this, we have the outside wall temperature, temperature of the environment, outside heat transfer coefficient. So if you take a look, there you go. Absolutely perfect, beautiful, beautiful summary of heat transfer across the wall. Excuse me, heat transfer from a fluid inside to outside. Okay, let's see what else we have here. Uh-oh. So I guess I wrote these. Let's see if we rotate clockwise. Let's see if we rotate clockwise, what we'll get. We ain't getting nothing here. Let's try counterclockwise. Okay, we start again. We zoom on down. Uh-oh. I guess everything's been rotated. I tell you, modern technology will clobber you. There's a beautiful view there. And let's go over here. I need to get back into page mode. I guess one of the ways of getting back to the page mode is to newt that, perhaps, and maybe I get into page mode now. So what we have here is a summary of the equations. Convection, this is just a rewrite of what I had written. Convection, inside fluid, conduction through the wall, and convection outside fluid. These Q's are all the same. Q equals Q equals Q equals Q. Okay. So therefore, we go to this situation. We rearrange everything by simply dividing through all those equations. And then we add up. And what we find out, we have T fluid minus Ti, Ti minus To, To minus T out. When we add this side, we have the overall temperature difference, fluid inside to fluid outside, right? And then what we have here is Q divided by 1 over this term, and then this term, okay? Or we have this situation, this is a basic heat transfer from a fluid at temperature, heat transfer through the wall, outside radius, whatnot. Absolutely gorgeous equation. And we simply write it Q equals inside coefficient, overall heat transfer coefficient, inside times area inside, T fluid minus T wall, where you got this massive thing here, inside heat transfer coefficient. Okay? Or we can write it out based upon outside heat transfer coefficient. Outside heat transfer coefficient is based upon the outside area. And what we have here is the overall heat transfer coefficient sitting here. Now we worked through an example problem here, which was kind of pretty cool, right? See, getting back here, we haven't pointed it out. This can control, or this can control. We're talking about controlling heat transfer coefficient, controlling heat transfer mechanism. The reason why you want to identify which ones control is because you might find out that making changes in the other two won't matter to you. So I run through a few calculations, and I have set up a problem, 1 over 300, and then I got this mess over here. So I wind up with three numbers here, 0.0333, 0.009, 0.05. And so my question is, which one of these is the controlling heat transfer coefficient? Well, this is, if I take a look, this is 3 zeros 5, and this is 2 zeros 9. So this number is far larger than this number. So the condensing steam doesn't really control much. I can make all kinds of changes in the steam side, and the effects would be very modest. However, if I come in and take a look at the conduction part, I see the conduction heat transfer coefficient, or the conduction part of the heat transfer, is fairly large number. So this is perhaps a controlling heat transfer coefficient conduction. And here you see that this is actually a very reasonably large number as well. You have 2 zeros 3. Over here you have 2 zeros 9. This is the one that is fairly unimportant. The controlling resistance is by the steel pipe. Now then, we go in and do the problem again. Okay, let's try something else. Let's try copper pipe. And we go in and we run through the calculations again. Now with copper, I see the steam is still fairly unimportant. I see the copper has significantly reduced the resistance there. And over here, so the controlling resistance here would be perhaps the inside heat transfer coefficient, or wherever that value was from. So we see the cooling water is controlling the heat transfer. This one's controlling. So we start making changes there. Then we throw in fouling levels, okay? And we throw in several fouling factors of 0.01, 0.01, and quickly we can see which one's controlling. Well, if we take a look, this was our convection last time, and we also have this here. So what happens is the fouling factor. The first fouling factor is the controlling resistance, right? This fouling factor is not controlling. This fouling factor is controlling this 0.01. So fouling factors for a shell and tube heat exchanger. Maybe you don't understand fouling factors, but you will eventually. Give you a quick look. Your teeth you have to have cleaned every 6 months or so, maybe. Go to the dentist every year, and maybe more than that. But your teeth foul, and you got to go have them cleaned. That's an example of fouling. Maybe you have a yellowy, a yellow layer on your teeth. You get it removed because you drink too much coffee, smoke too many of them cigarettes. Anyway, laminar flow, Turbulent flow, you remember that from fluid mechanics, very important here. Driving force, log mean temperature difference. This is the derivation of log mean temperature difference. If I really wanted to worry about heat transfer, I'd probably know that derivation, but I don't require you to know that derivation. So we have a log mean temperature difference, which we will show you later, perhaps. You got two positions along a heat exchanger. You got one end, which is zero length, and then the exit, which is there's been a length change, right? So you take the temperature difference at one end between the hot and cold fluid, take the temperature difference at the other end, hot and cold fluid. That gives you the delta TO, and then we take minus delta TL, and then you take the ln of the ratio, and that's the delta T log mean temperature difference. Wonderful item. Thermal entry regions, very important. You should read up on thermal entry region. You should know wetted perimeter and hydraulic diameter. And making further on down here, we do a calculation. Hydraulic diameter. Wetted perimeter is variable. Should watch out. It's a little different for heat transfer than fluid mechanics. So hydraulic diameter and heat transfer is different than hydraulic diameter and fluid mechanics. Non-condensables. Oh my goodness gracious. So quickly we go to non-condensables. Non-condensables are first-class pain in the neck, okay, and they often need a purge. Obviously, if, say, you're running a condenser unit where you're condensing water, if you have air in the condensing water, then the air is not going to condense and form a boundary, and the non-condensables build up with time and cause significant effects. Usually requires you to have it usually results in poor performance. So you need to, non-condensables on scaling, you need to vent non-condensables and inerts. And this could be a major problem when you're scaling up, going from, these heat exchangers you got to recognize can cost you $1 million, without a doubt. So you need to pay attention to their construction and how they're put together. And they're quite large as well. And as a result, you can have leakage. Pipes leak. They leak in and they leak out. Anyway, this is heat transfer correlation for inside heat transfer coefficient. This is basically a Nusselt number. In here is a Reynolds number, a Prandtl number, and a diameter over length of the pipe diameter ratio, and a viscosity ratio. The first thing you want to know is the laminar flow. It has 1/3 exponent. First thing you want to know. Second thing is you have a D over L effect, which does not appear in turbulent flow. And you have this viscosity ratio that is practically worthless to calculate. If you wish, yeah. If not, that's fine too. Calculations maybe plus or minus 12%. I don't think it's that good. It could be even worse. Going on to, I'm just telling you the truth here, guys. You don't expect me to lie to you. Now we go to turbulent flow. Again, we have the Nusselt number. We have the Prandtl number. We have the viscosity ratio. And here we have 0.8 power Reynolds number. The lead coefficients changed significantly. Remember what the lead coefficient up there was? Lead coefficient up there was 1.86. Down here it is 0.072. So a couple things have changed on you here. The lead coefficient changes on you, and this exponent changes on you. There is no length to diameter ratio effect. Diameter to length ratio doesn't exist. Anyway, Kern's great book. And when I was growing up, which was a long, long time ago, I grew up in prehistory. I want you to know that. I'm a very old man. Okay. First thing, just kidding. First thing, approximate overall design coefficients. You can't fool Mother Nature. So overall heat transfer coefficients will be floating around here. And this is dirt factor of 0.003, allowable pressure drop 5 to 10 psi, cooling streams. This is for coolers, and this is for heaters. And the first thing you got to recognize is these guys get a minus 100 on Tatterson's test because there ain't no damn units on this sucker, right? See, there's no units. You got the fluids, you got hot and cold fluids. So these heat transfer coefficients can actually be very miserable, I'll tell you, very, very miserable. But this is BTUs per hour foot squared degree F. Anybody would know that, because those were the only units that was used back in 1950. We never heard of the metric system back then. You know, imported communists. Anyway, the metric system failed in the United States. We, as engineers, use all units, all the units. We don't mess around. We can take them all coming. Okay, you got to recognize units are your friends. They're very important to keep track of. And of course, Kern gets a minus 50 because he doesn't have units. Shame on Kern. Anyway, you probably never see this in your life, but this is tube sheet layout. Shell and tube heat exchanger. Tube means many, many tubes. Shell means one shell. So I have 3/4 inch tubes. You guys in mechanical engineering just love this kind of stuff, man. It makes your day, float your boat. Anyway, we have triangular pitch, which we'll get to a little later. We have 3/4 inch OD tubes and a 16th inch triangular pitch. We have the shell diameter. Inside shell diameter. Outside shell diameter don't matter now. We don't care about the outside, except it's got to be thick enough to be able to handle the pressure. And so if I have a 23-inch shell sitting here, I'm doing a one pass, right? I would have a possibility of putting in 442 tubes that are 3/4 inch. Isn't that fantastic? That's fantastic, I'll tell you. By the way, Kern was 1950. That means it was probably written between the 1940s and the 1950s. This is the textbook, or the material in the textbook that beat Hitler. That's how great this stuff is. I'll tell you. I'll tell you. And one of the things about old stuff, it's great. Right? Old stuff means it's a masterpiece. Old stuff means it's a masterpiece. Heuristics, that's sort of like rules of thumb, but rules of thumb are dangerous. Heuristics, you want to exchange heat, you want to, with an allowable pressure drop, you want to do it safely. And heuristics will unfold as the course progresses. There you go. I should go back here for a second. Tell you a sad, sad story about dirt factors here. By the way, there's another fundamental equation I didn't mention here. It's not written here, but it's a very fundamental equation. Laminar flow plus heat transfer equals many problems. Got that? Laminar flow plus heat transfer equals many problems. So the whole goal in life is to stay turbulent. You want to remain turbulent. You want to maintain chaos. Coming right up here, we go up here to these dirt factors. All right. And one of the things, it's way up here somewhere, huh? One of the things you should recognize about dirt factors, let's go down here. Delta T. There you go, entry regions. Go up here. Sad, sad story about dirt factors. The CHEN company making heat exchangers, right? So they made a heat exchanger, sold it. And it was sold and used for about 10 years. And the company who was using the heat exchanger sold the heat exchanger to a used equipment manufacturer. I don't know, they were dismantling the plant, they were changing the process. Anyway, they sold this piece of equipment to a used equipment manufacturer. Now, the used equipment manufacturer refurbished it, and that means they cleaned out the inside and painted the outside and scrubbed up the boilerplate. Used equipment typically sells for about 80% new equipment. Okay, so there's not much savings when you buy something used. Where the savings come from is you can have it immediately. In other words, they don't have to get into a queue. They can have it delivered in a short period of time. And that's the major advantage of using used equipment, is you can have it right away. If you go and build a thing, you may take 6 months to get it to you. Anyway, so this one company builds a heat exchanger, gives it to another, sells it to a company that uses it for about 10 years, and then resells it to a used equipment manufacturer. They paint it up, clean it out, and sold it. And they sold it to another company. And within, say, they started it up, put it in the process, started it up. And within maybe, I'm not sure, I don't know the history exactly, but 10 minutes, the plant exploded, basically. And so what you have in there is you have residue surface material, which is called dirt, characterized by a dirt factor. And what happened is the heat exchanger detonated on everybody, and apparently took out 5 city blocks. Now, that's what the story I tell. And the company who made the heat exchanger originally was either called Patterson Kelly or Kelly Patterson. I'm not so sure. But they quickly get out of the heat exchanger business. What happened was that they didn't clean the heat exchanger sufficiently enough. There was a residue left in the heat exchanger, the used equipment company guys. There's a residue left in the exchanger, and the second company didn't realize exactly how much residue was in there, or what was there actually, and it caused a big kaboom. So the problem with surfaces is surfaces is a first-class pain in the neck, and you can never hardly get surfaces clean. You got to you got to wash a long time, many times, to get a surface clean. So I have an experiment for you to do. Now, throughout this course, I'm going to give you small little experiments to do. It's just a casual experiment that you don't have to really do anything except look at it. I want you to drink a glass of milk. Now, that ain't too hard now, is it? So you drink a glass of milk. And what do you see after you drink a glass of milk? Set the glass down. You can see a residue of milk left on the surface of the glass, correct? That's the famous no-slip condition. Okay. Fluid at the boundary moves at the velocity of the boundary, no-slip condition, right? So I want you to rinse it out. I want you to, not too hard now, I just want you to fill the glass up with water again. Don't swish or anything like that. Just fill it up and then dump it out with water. And you'll see the milk still there. A little less, but the milk will still there. I want you to do it again. I want you to do it again. And see how many washes it takes for you to get that surface to the point where the milk is no longer there. And this residue stuff from used equipment can come back and, how can I say this, kill you. Okay. Nature has a great habit of reaching out and killing you. Okay. One of my famous statements. So anytime you buy used equipment, you better damn well make sure it's clean, or make sure you knew where it came from, because the surface carries with it a contamination. And again, I would say it takes 5 washes to get the milk off your cup. Now, in the chemical business, in the chemistry purity business, you got to get the surface chemically clean. That means you probably need 8 or 10 washes to get it chemically clean. Thermal entry region, you can read about that in your fluids book. Read about that later elsewhere. Anyway, So let's move ahead. Laminar flow plus heat transfer equals many problems. Overall heat transfer coefficients, Kern's book, there you go. So what the devil do we have here? The other thing I want to point out is allowable pressure drop. See the allowable pressure drop? That's not really what it says. It says utility bill. It takes power to run a heat exchanger. So I have pressure drop times volumetric flow rate. Very fundamental equation you should have learned in fluid mechanics. Again, flow rate times pressure drop equals power. Now, all of us pay a power bill at the end of the month, right? Our electric bill, that's a power bill. So it takes power to run a heat exchanger, and it costs you. And it's volumetric flow rate times pressure drop will give you power requirements to run the heat exchanger. You want to have access, assess the equipment operating conditions, allowable pressure drop, fouling, erosion, corrosion, what's happening, why not, preventive maintenance, is it working, leakage, potential problems will be discussed. Moving right ahead. So we're going to talk first about heat exchangers with no phase change. Okay. Well, you're transferring one from one fluid to another, allowable pressure drop, no hazards, minimum costs, reliable equipment. Numerous factors to be considered are service life and reliability of the unit, fouling and temperature, right? You want high tube count because that gives you large heat transfer coefficient. You want leak-free operation. You want to be able to get to accessibility of the heat transfer surfaces. You want to have access so you can see what they look like and so you can clean them. You also want to have easy replacement of the tube bundle. Oftentimes, shell and tube, we're going to be talking about tube bundles. We got to go into the temperature and pressure and corrosion limits, costs. And we have your friends of mine, erosion and vibration. The mechanical engineers, you guys should get off on this. You spend $1 million for a heat exchanger. You installed it, you started it up. And it would last maybe only an hour or so before it vibrates apart. That means vibration analysis wasn't done very well. And anyway, so I got to stand up with the operating temperatures and pressures, stresses, expansion and contractions, corrosion, erosion, microbial deposits, fouling, ease of joining tubes in the tube sheet. Yeah, that's a biggie right there. Proper thermal conductivity, standardized tubes and materials. Those are some of the considered temperature profiles, right? So this brings us up to our first shell and tube heat exchanger here. Let's get this, though. This actually turns out to be important. Temperature profiles. Typical operations is countercurrent. Typical operation is countercurrent. This is less heat transfer area needed, and it's perhaps the most used. Countercurrent operations is the best. Co-current operations, well, higher areas are needed. Not usually thought of as favorable. So you have countercurrent, co-current. But co-current is used when? Let's see if I have it here. Oh, I don't have it here. Anyway, let's take a look at this little jewel here. Clockwise, there we go. Tatterson Foundry and Machine Company. Again, this is taken from Kern. This may be before Kelly Patterson. Anyway, what we have here is a shell and tube heat exchanger. We first have the shell. You can see the shell. And we can see the tubes. The tubes are running right here. So we have a shell containing a whole bunch of tubes. And this is called the tube sheet. This is what the tubes are fitted into. And this is called a channel cover because it covers a channel. This is also a channel cover because it covers a channel. So what happens is the fluid comes in here, can't go through the tube sheet, but it goes through the pipes. So So it zooms all the way down there and makes a U-turn, comes back out here. It can't leave this tube and go into this tube. That would not work very well, right? So it exits these tubes and enters these tubes here. So you have one pass here and a second pass there. And you have the inlet nozzles. This would be an inlet nozzle, perhaps, if the flow is coming in. This would be an exit nozzle. This is also called a nozzle, and this is also called a nozzle. They got to call it something, right? Might as well call it a nozzle. It's an unuseful term. Now then, these little jewels in here are called baffles. All right, the baffles in here. We'll get to those a little bit later. They're put in there to direct the flow. You want the flow, there's two types of flow here. I mean, two flows. There's pipe flow, basically, or tube side and shell side. Shell side flow, perhaps the stuff comes in here, comes down. You want to go across the tube bundle. This will be a bundle of tubes. Notice the tube sheet and the shell are attached to each other, right? But you hope the inlet flow comes across the tube bundle and goes zoom, 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 and the way you get out that way. And the baffles, that's what the baffles are trying to accomplish. Oh, when I was an undergrad, we had a heat exchanger. It was pretty funny as hell. It had these baffles in there. And what happened is the baffles were so bad, we injected the fluid in the fluid. Shell side, we injected dye, see what would happen. It's visual glass shell. And we injected the dye, and the dye went right through. It didn't go across like that. It didn't do that at all. That's because the baffles were poorly designed. There was a lot of leakage in there, baffle leakage. In other words, flow bypassed the baffles. In other words, it'd go through here, go around the tubes. That's not good. Now there's a major problem with this heat exchanger, and the major problem is if the tubes expand differently than the shell. It was built at a certain temperature, but if the tubes, if you're going to get them hot, they'll expand. And they may expand at a different rate than the shell does, which isn't a great idea. What you want to make sure typically is the thermal expansion coefficient of the tubes about the same as thermal expansion coefficient of the shell, because you don't want them to expand apart. You got what I said? Expand apart. Nature has a habit of reaching out and killing you. So, well, anyway, to prevent the expansion problem, all right, they have what is called a floating head. Now, I hope you don't mind me using that word head. It's see, right there it is, floating head. Anyway, floating head. See, this thing right here is called the head, and it's not attached to anything, so it's floating, right? And that means the thermal expansion of the tubes is such that it can expand freely. They got a lot of expansion in here. In fact, this is probably a bad design. There's so much stuff here. So the stuff comes in, the tube bundle is floating. This is called tube bundle, right? We already said that. And so that takes care of the expansion on this. This heat exchanger could work really well if there's not much heat transfer going on or not much temperature changes. This one has a floating head. It allows for the tubes to expand in a different way than the shell. So everything's wonderful here. Right. Nope, not everything's wonderful here at all because the shell is being wasted. See, this thing's going to cost you $1 million. So you want to try to have it as efficient as possible. So you have this shell volume in here that has no heat transfer surface in it. So you're wasting money here, gang. So then you pop down to this job. This is floating head. This is a pull through because you can pull it all the way through. It runs right on through. You do that in case you want to easily clean something, right? Say you have fouling. Well, if I was to clean this heat exchanger, I would remove this channel cover here. I remove this back channel covers, these two. And the tubes would be open for me to clean them, right? The problem is the shell wouldn't be open to clean them that easily. Cleaning the shell is tough. So in this case, I could pull the bundle. In other words, I have enough service area or volume that I unbolt here and I pull. And I can pull that whole bundle of tubes out. So the distance of the heat exchanger is actually somewhat doubled. And that gives me access to the tubes and lets me clean better in case I have severe fouling. Tube side, shell side. This is shell side. Shell side fouling is a pain in the neck. You want to put the fouling material inside the tube. First requirement of design. That way, a design suggestion, I should say. And that way, tubes are real easy to clean. Shell is quite complicated to clean. The flow pattern in tubes is real easy. The flow pattern in shell side is quite complex, quite difficult to specify. So next we go on to floating head. There we go. Floating head. Now the problem is this ain't pull through anymore. Can't pull this through. So here we pull this through, get access to the tubes. Here we can't pull through because we got some problems here. Maybe we can do some flange work here and here so that we could possibly pull it through if we wanted to, but anyway. I don't know why there's this double cover here. I guess I think that this is an extraneous drawing in here. Anyway, the difference between this design and this design is I have filled up the shell side here. Here I have this vacant shell side volume. Here it's been filled up with tubes. And so I have a much more effective heat exchanger. And lo and behold, look at what we got here. We have FEMA strikes again. Uh-oh, wrong turn. We back that far. Boy, have I messed that up, huh? We flipped it around so much, are we going backwards or forwards? Oh, we're going down this way, I'll tell you. Go to the last page. No, don't want to rotate. Oh. Keep on rotating, you'll eventually get it, right? We've already talked about those, and so we're moving right along. Quickly, we find we run into FEMA. You don't know who FEMA is? Oh, geez, oh man, guys. It's Tubular Exchanger Manufacturers Association. So all the people that make heat exchangers, I'm not sure if they haven't all moved to China. Good thing we have, an emphasis on returning things to America, huh? Maybe we can get it back. I'm not sure. Yeah, anyway, we won't pick on China here. We have FEMA. So FEMA is Tubular Exchanger Manufacturer Association. They're the group of people that make heat exchangers. And so what you can have is you can have a front end, you can have different shell types, and you can have a back end. Okay? Isn't that fantastic? Got any better, I wouldn't know how to handle myself. My battery is running low here. Let's see how much I got left. I got 2 hours and 33 minutes left. I got 66% remaining. So if you want, let's take a look at this. Let's go with a BEM, a beam heat exchanger. That means I would have this as my front, this is my shell type, and this would be my fixed tube sheet. So that's how I can have an NKU, right? Which for a reboiler wouldn't be a bad idea. U-tube, see that? There's no return bend there. I mean, there's no U-tubes. Problem with U-tubes is bending the tubes such they're not crimped. You ever try to bend a tube? It can be, how can I put it, quite humiliating if you... Yeah, give that to your children to see if they can do. Anyway, heat exchangers, you should look at this here. You got to recognize heat exchangers got a lot of parts. Right? Got a lot of parts. Heat exchangers have a lot of parts. Especially this one. What is this here? Heat exchanger parts. Oh, nothing special. This is an AES, and that one's a beam, BEM. What it might look like. Look at that. Kind of interesting. We have a floating head here. Actually, no. Is this floating head? No, it's not. Ah, look at that. There is no there is no floating head here. What you have here is an expansion bellows on the shell. These things are probably very sensitive. You don't want to damage these things. They got to move, so they got to expand and contract. They got to maintain pressure. So when you're manufacturing heat exchangers, there's probably 4 hold points. What the devil is hold points? Well, if you're going to build one of these things from scratch, you got to figure out what exactly how you're going to pick a vendor and whether you can trust the vendor or... So there's 4 hold points for heat exchanger building and construction. First, you want to visit them just to get acquainted. You want to see if their welders are actually certified, look at their welding capabilities, look at their background, see if they actually know how to weld. I mean, I can weld. You don't want to buy my stuff, I guarantee you. I just, these guys, you know, they lay down a really fine bead. You know, hopefully they'll lay down a fine bead. The first thing you want to do is you want to see about their welding capabilities, their certification, and how they store their tubes. Now, if the tubes are up on a rack, that's pretty cool. The tubes up on a rack. However, if the tubes are laying down in a pool of water on a concrete floor and there's about 30,000 of them, you probably want to turn around and walk out. You don't want to deal with somebody who can't keep their materials protected. Okay, they should be, you know, in situations where they're not in a corrosive environment, off the floor, no moisture, kept clean, that sort of thing. Watch, and you don't, you know, once they touch a tube, it's dirty. That's the first hold point, just a general visitation to see if everything's arranged, whether they're organized, where they actually can chew gum, walk, and think at the same time. So there's 3 things: walk, chew gum, and think at the same time. Second whole point is you have a tube sheet sitting here. There's a tube, and it's a sheet of tubes. You want to watch how the tubes are inserted into the tube sheet. You don't. There is no pounding with a hammer. The tube opening should be free of burrs and should be no lubricant used. Straight insertion. No damages, no forced tube sheets. Well, you got to force it somewhat. So, and then you probably want to watch them how they weld. There's a little weld that could be around that tube sheet as well. Anyway, that's the second hold point. The third hold point is watching how they insert the tube bundle into the shell. That's the third major hold point in the construction of a heat exchanger. How they insert a tube bundle in the shell. Okay? And the fourth hold point, what would be advantageous is you would insert, oh, did I do that wrong again? Takes some time, does it? We went forward that time. Holy tamale. So you want to watch how they insert the tube bundle into the shell. You would like to insert it vertically. All right, the shell would be vertical and you would insert vertically downward. That was perhaps the best. If you insert it where you insert horizontally, that'd be a first-class pain in the neck because you got a lot of dragging going on. You can't use any lubricants either. It's not allowed. It's not a good idea. So that's the third hold point. The fourth hold point might be to watch how they handle this expansion joint. This expansion joint, you want to be there when they pressure test a bellows. Should recognize what we're talking about has implications through all kinds of equipment, right? Right now we're talking about heat exchangers. Well, what about something else you're building, like a distillation column or like a jet engine or a rocket, right? Whenever they're making something for you, you want to go visit, and you want to visit key parts of the manufacturing. So you want to, give approvals, right? Hey, you can be suckered, no doubt about it. You can be suckered into buying crap. And like I said, for $1 million, you got to monitor it and be hell. You pay $1 million for a heat exchanger and it shuts down within the hour. Oh, you're going to be famous. You buy a heat exchanger, shuts down within an hour, you're going to become company-wide famous. Got it? Just thought I'd tell you that there. Anyway, so let's move along. Oh, look at this. I guess I got to do a rotation on this one too. Wrong direction. Wrong direction. Wrong direction. Eventually I get it right. So you have principal. See how it's spelled? P-A-L, not P-L-E, principal. So you got tube sheet, U-tube, packed lantern ring, floating, internal floating head, outside packed floating head, pull through. So you have various yes-nos going on. So you're comparing designs here, folks. Comparing designs here, folks. You guys probably thought that designing heat exchangers was one time and done, huh? No. Various exchangers for various types of jobs. There's three classes of heat exchangers. Our class goes into petrochemicals and severe power industry stuff. Internal pressures might be 10,000 psi. Did I ever tell you what 10,000 psi looks like? Did you see it? 10,000 psi steam is colorless, odorless, noiseless, very small, can't see it. It'll cut you in half. What happens is, with the power industry, their walls for their stuff in the power industry may be 6 to 8 inches thick. And they spend a lot of time making that wall good. And what will happen with steam is the steam will eat a little pinhole through 8 inches. And then it'll come out on the other side, just as a little tiny streak of steam, except it's 10,000 psi, minus the little bit of pressure drop that it had to endure going through that little hole. So by the time you're walking through it, it may be 8,000 psi steam. Well, anyway. Make sure when you're walking around high pressure equipment, all right, you always carry a broomstick ahead of you. And you get the handle adjusted so you have a handle on the broomstick handle to keep you from, you have that from head to toe, head to foot, all right? And you keep that ahead of you. And you walk slowly, not too fast. And for some reason, that broomstick suddenly comes apart. You want to stop. Stop. Right. The only problem is if it comes apart around where you're holding it. Anyway, that would be the only problem. Anyway, so we got various designs, various things. Look at what we have here. rear head type, whatever that is, removable bundles, replacement bundles, individual tubes, replaceable. Nah, you don't want to replace the tubes. That's kind of on the dumb side. You want to plug them and leave them. Tube cleaning. Look at all hydraulic cleaning. Woo! I tell you, you can't get much better than this. I'll tell you, this is absolutely wonderful stuff. Where is this coming from anyway? Is this from, oh, this is from Gupta, yeah, I think. Ah, characteristics of tubing. Oh. Did you know that 1/8 inch tubing is not 1/8 inch? Let's see, we have tube over here. We have 1/4 OD tube. All right. Different wall gauges, different internal areas in here. Anyway, Bingham wire gauge. Anyway, internal area. Oh, look at this. Golly. Radius of gyration, moment of inertia. Is that for the vibration analysis? Okay, so this, oh geez, did I screw up again? I tell you, they ought to train these professors better, I'll tell you. Yeah, let's see where I'm at now. Major considerations. I'm probably down in here. There you go. I think that's where we were. And then we got to go here. We got to do this thing here. There you go. There you go. So this is the TEMA thing. See if it's TEMA. Yeah, scope of TEMA standards. Now TEMA, you got people beyond TEMA, okay? Maybe they're parts associated with it. This is what they all agreed to. You can go up to 3,000 PSI. I already told you there's stuff that goes up to 10,000 PSI. The higher the pressure, the more efficiency, I guarantee you. So you can have 300 PSI, 3,000 PSI. You know what that is? 3,000 PSI. That's 200 atmospheres, right? Roughly 200 atmospheres. Right? Anyway, it goes up to about 20-inch shell, inside diameter shell. We don't talk about wall thickness here. And then for some strange reason, it comes down 60 inches here. You can go to 1,000 PSI. Now, this is probably scope of TEMA standards. That may have changed. That may have changed over the years. Anyway, if we, the important one right here is 300 PSI. See the line across at 300 PSI? There's two other major heat exchangers we're going to talk about. One is a plate heat exchanger, and the other one is spiral heat exchanger. Their upper limit is 300 PSI, right? So right across here. You can see those two other heat exchangers can work absolutely wonderful. But you can see what the shell and tube can do for you. Just to give you an idea. All right, and I already said you can go up to 10,000 PSI easily. So there's three types of heat exchangers we mainly cover, plus the phase change stuff. Upper limit on those other exchangers, those other major exchangers, is 300 PSI. And you can see you can go to 3,000 PSI with shell and tube. Okay, let's see what else we got. Oh, yeah. Okay. So what happens is you have the shell here, and then you have the baffle, and the baffle and the shell really don't touch, right? You're sliding it in. Here we got something. Isn't that cool? And, you know, from the point of view of engineering, they ask what the hell that is. The engineers, oh, hell, they don't know what that is. So they go out in the shop. They ask the shop guy, what the hell that is? And the shop guy, he says, it's an ear. What do you expect? Do you think these engineers know anything? So they call it an ear. Why? It's because what the shop people called it. Question for you: why is the baffle notched? That's a test question right there. What do you think? You tell me why the baffle's notched. Okay, this is called a baffle window up here. It's an opening. So when I look at this baffles in here, I got baffle spacing, and I got support, whatever that is. And I don't want to have two tubes rub, because when two tubes rub like that, they have baby tubes. Okay? Just kidding. You don't want to rub it too thin. I mean, that's constant rubbing in there, and eventually you'll make a weak point in the tube. And of course, you got to watch out for the bend, because you try to bend the tube, you'll crimp it. So that's your assignment. You want to go bend the tube in a machine shop somewhere. Got it? This is from Yodel. Fantastic book. Put you to sleep in about 5 minutes. And then we have this thing right here. And quickly you see the outer tube limit. Outer tube limit. Outer is OTL. Outer tube limit. And you have the different baffles in here, and you have sealing strips. What the sealing strips do is to force the flow across the tubes, not around the tubes. Now, sealing strips was all the vogue, but again, the sealing strips indicate the lack of use of the full volume of the shell. So I think sealing strips are probably out. They may be around for some exchangers, but modern day shell and tube exchange, I don't think use sealing strips. But that shows the tube bundle. See the bundle of tubes? You have the tie rods or support rods, and you have the baffles. The baffles support the tubes. The tie rods hopefully keep the baffles in place. You don't want to have the baffles walking, right? Because this baffle and this baffle could join together, really cause havoc, right? You don't want walking baffles, although I'm sure they do move. Hopefully they don't. Okay, moving right along. What else do we got here? Oh, yeah, look at all these types of expansion joints. I stole this from Perry's handbook, Chemical Engineering Handbook. High pressure Toyota bellows, bellow types, Toyotas. Anyway, these things obviously have to do the thermal expansion aspects to a exchanger. They also got to take the pressure. And the two don't go well together. So these are things that are quite sensitive, and you should be careful. I think we're done for about the first hour, so we got 1 more hour to go. Looks like said I had 2 hours and 6 minutes remaining. I got 55% of my power left. So I'm just looking at my battery here. Moving right along, let's see what else we got in here. Okay. What diameter for shell? Well, you want small diameter shells because they're less costly, right? And that means you just have long pipes. You probably need less wall thickness. Tube diameter goes down. Tube sheet diameter goes down, which is less costly. Number of tube connections decrease. Longer tubes cost less in terms of total heat transfer area than the short tubes. However, longer shells mean higher pressure drop. Floor space and layout could be a problem. You're going to have to pull that bundle at some point, and you need to have floor space for the bundle to be pulled. There you go, laddie. You're going to pull your bundle. Push in, take out. Long tubes require longer cleaning space. Vibration problems also increase with longer tubes. So there's a trade-off here, different things for different folks. And these are interesting design questions, right? Now, if you've been designing for quite some time, take no problem. I want to go clockwise, don't I? Yeah, clockwise. Which brings up square pitch. See the square? brings up triangular pitch. Here's a square pitch rotated, and here's a triangular pitch with cleaning lanes. See, there's not really cleaning lanes in here. So what happens when you have tubes vibrating? Well, you can sew. You get flexible wire and sew the tubes together. How about a corkscrew? Coming in with a corkscrew. How about rotating the tube bundles so the tubes don't vibrate as much? Why do tubes vibrate anyway? Oh, yes. Let's do a rotation here. Which way do I want to rotate? I want to counterclockwise. See, this shell comes in, this nozzle comes into the shell. There's a bunch of tubes down here. You have high velocity flow hitting the tubes. This is not good. So you do an expansion nozzle on it. This possibly will lower the flow. I don't think it'll lower it that much because the momentum of the jet will continue. And it smacks up against those tubes. Okay, only part of the tubes. The rest of the tubes are not slammed that easily. So I'm very much sensitive to what velocities are coming in to hit my tubes, because that could set up a whole bunch of tube vibrations going on. So a number of things I probably want to do is make sure the expansion bellows is large enough to let the flow in. You can have a belt. Is this what they call that? A jacket. I call it a belt. Ah, down here's a belt. Okay, gotcha. This is more of a belt here. Anyway, you have side entrances where the flow comes in, goes around the jacket or belt, and is easier fed. It reduces the velocities. This could probably be a lot bigger than the nozzle area, a lot longer. Or we could have feed this way coming in from the belt. You know, flared nozzles, modified shell contrast. There you go. There you go. So we took care of that. We said several ways of solving tube vibrations, and then we're going to do several ways of reducing the cause of tube vibrations. Then we got to talk about that tube sheet here, which I want to rotate clockwise. Oh, geez, I lost my page. T50, I'm already at the end. Wow. Let's go up here, noncondensibles. Let's go back up here. I'm going to try that again. I'm going to rotate clockwise. That's counterclockwise. That's clockwise. There you go. Anyway, did you know that you can over-tighten or under-tighten your tube sheet? You know, you got to watch out for your tube sheet. You got to have it tightened just right. There's a lot of things in engineering that sort of resembles Goldilocks. Goldilocks and the Three Bears. Not too hot, not too cold, but just right. So whenever you're talking about tightening your belts on your tube sheets, right, your flanges. So you have your flange here. You could possibly under-tighten, where you could possibly bow your tube sheet in such a manner that the tubes expand and you haven't got them tightened up enough. And then this is convex, overstressed. May bend, pinched gas, lots of reasons for that, right? That's not good. That's not good. That's not good. Over here we have concave. Lots of reasons for that. So that's not good. That's not good. Okay? So you don't want, it's Goldilocks. Not too tight, not too loose, but just right. Now then, what do you do when the two things mix? Basically, you'll probably wind up dying. It never does work right, does it? This is everything you wanted to know about heat exchangers, right? Anyway, try counterclockwise. There you go. Double tube sheet. Now then, you have obviously the shell side and the tube side. You have this here. So you have one tube sheet here. The tubes had to go through that tube sheet. And this is a really great joint in here, welded or whatever. And then after you get it again, you got to do that in there with this other tube sheet. So you have the tube side fluid, and you have the shell side fluid. Over here is the shell side fluid. And in between here, you have a vacant. There's nothing in here. And then you have a place where you have for drainage. So what will happen, and the reason why you would have a double tube sheet, is if there is leakage here, it leaks to a place and then comes on down. And if there's leakage here, it leaks to the place and comes down. Now they may mix down here, which may not be a great idea. And actually they should probably have built a better design than this thing here. Anyway, that way you keep the material from reaching each other, because you know what they're going to do when they reach each other. They're going to do something that you won't like, right? So let's take a look here, right, exactly what the possibilities are. Conditions that might require double tube sheet, and the one I like is right in here. Safety. Streams might ignite or explode when mixed. There you go. You go to work and suddenly the two streams are mixed and you come home in a pine box. Right? That ain't good, coming home in a pine box. Corrosion, health reasons. One stream's lethal. Mixes with the other stream. Lots of reasons why you might have a double tube sheet. You don't want the possibility of these streams mixing. And look at this. By Job, look at that. We got the source of Yodel 1973. Okay, moving right along. Double tube sheet bending. Ah, geez, this is all kinds of, what do you guys, mechanical engineering type stuff? Geez, oh man, aren't you guys raking it in here? And to think you're being taught by a chemical. Oh, God almighty, huh? Geez, oh man. No respect, huh? I'll tell you, this thing is never going to work. Okay, anyway. The orientation on this doesn't matter. Let's take this one right here. This is a 6-pass. These are channel covers. So it goes in at 1. It comes out at 1. Goes into 2 because it's the only place it has to go. Comes out at 2. Goes in at 3. Comes out at 3. Goes into 4. Comes out at 4. Goes into 5, and comes out at 5, goes into 6, and comes out at 6. That's a 6-passer right there. That's determined by the channel covers. This is the front of the exchanger, and this is the rear of the exchanger. Isn't that fantastic? It's kind of interesting. Let's take a look at this. It goes in here is the front of the exchanger. It comes out there, goes in here, all along there, comes out there, and goes in here, comes out here. It's kind of interesting. Anyway. Oh, jeez, oh man. Isn't that fantastic? This information, you'll probably be watching this over the 4th of July. This is so stunning stuff. And you probably will give up watching fireworks to stay home and read my we go over this stuff. I'll tell you, there's nothing better than heat exchangers at the 4th of July. Here's some more pictures. Look at that. No tube in window. remember, this is the baffle window. This is a baffle window. This is a baffle window. That's where a tube is fairly long and it's undergoing various flows. The flow is hitting it, and it's going parallel, and the flow is accelerating away or moving away. I don't know if it's accelerating. It's probably decelerating away. Who knows what it's doing? It's probably decelerating away. Anyway, a place for good vibrations. A Beach Boy song with vibrations. So we have the tube sheet, tube window, right? We have tubes through. We don't have any tubes. We don't have any tubes because if they were there, they'd be vibrating. That's not good. Different different nozzle designs to prevent high-speed flows from hitting the tube bundle. Of course, we could put in here an impingement baffle. Baffle is a piece of steel or piece of plate put in. And impingement baffle would be maybe a sheet of plastic in here to keep the high-speed flow from hitting the tube bundle. Yeah, various types of. What's really funny, I was lecturing away, giving this course, and I said this is called a donut baffle. Right, this is a baffle with a hole in it. And I would say nobody uses these. Okay, I was like, that's a kind of goofy design. Guy in the back of the room raised his hand. We have them. Okay. I lost that one. Yeah. Isn't it fantastic? You get so damn old you don't care. Fouling. There you go. Now, fouling, first off, you should recognize it's process specific. Now, you can buy a heat exchanger, shell and tube heat exchanger, install it, and never clean it, ever. Okay? Just the fact that you have such a clean operation and nothing is going to cause it to corrode. However, I've run across people, plant people, that have to clean their heat exchangers every 3 days. So cleaning a heat exchanger every 3 days, now that makes cleaning a very important item. So you got to recognize cleaning is often critical, right? You should recognize fouling specific, again, 3 days versus never. Fouling builds up with time, significant effects, varies with location. Inside the exchanger, dead zones lead to fouling. Well, you hear all this stuff, you want to try to prevent dead zones. Blah, 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 you want to try to prevent dead zones. Blah, 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 you try to prevent dead zones. That's a fairly worthless statement, by the way. You want to prevent dead zones. It's worth nothing. Nothing. Upper management doesn't understand that. Upper management doesn't understand that you want to have everything perfect. Now, this is what you say. You say, dead zones means lost profit. What? Dead zones mean lost profit. What? Dead zones mean lost profit. So now you got upper management's attention. Maybe they're just sleepy upper management. Who knows? But when you say dead zones are terrible, they're an engineering hazard. Well, so. But when you say dead zones is lost profit, or you could be more efficient, make more money for them. Forget about efficiency. Talk efficiency, that's sort of dumb. But you really want to talk about money. Efficiency is one thing, but you talk about how much money they're going to make with a more efficient system. Now you got them. If you got a resume, right, you listed all the jobs on your resume and how perfect and wonderful and what a dear John you are to everybody, and you don't have money on your resume? How much money you were in charge and how much money you saved? That's a strategic point in getting a good resume. Just to give you a little tip there. That's a freebie from me. Right? The way things are, my upper management only has one question for you. You can hear the question? Did you hear it? Let me tell it to you. Upper management's question. What have you done for me lately? Let me say that again. What have you done for me lately? Not what you did in the past. That's history. That's gone. We've already made money off you. Now we're paying you 150,000 a year. What are we getting back for that, son? Or what are you getting back for that, daughter? So there you go. You gotta. You can always say dead zones are bad, but then that's a bad way of saying it. You got to say that dead zones means lost profit. Anyway, you should try to eliminate dead zones. You can read that. Can you read? I hope you can read. Can you read? And here we got a picture of fouling. See if we get this. It seems like the rotation clockwise is the only one that works. The counterclockwise I get sent off to Zuzu land. So you plot performance index. So what's your performance index? Overall heat transfer coefficient. You plot that with time. And as it continues to get dirtier, it'll drop. So that means you should have online capability of calculating your heat transfer coefficient. Measure the temperatures in and out, you know the area of the heat transfer, and you know the heat temperatures in and out will give you how much heat was transferred, and the log mean temperature difference will be there in the temperatures, and you know the area of the heat exchanger, so it's an elementary calculation to calculate the overall heat transfer coefficient. You plot that with time, and then you say, it's got dirty enough that I need to clean. Right? So it's got falling off. Then you got to decide what's acceptable performance. You define what you want for acceptable performance, and then that specifies the day that you clean. Got it? Downtime, nothing's being made, so that's bad news. So then you come up here and start all over again after you're clean. But you want to basically, among other things, you want to take all the exchangers down at the same time and have, say, August, the time you clean heat exchangers, or springtime is the time February is the time you clean heat exchangers. You take one of the times where it's not critical that you be up and running so much, that's when you clean your heat exchangers. You clean them all at once, you standardize on one design and used everywhere. So 1-2 heat exchanger. One pass tube side, one pass shell side, two passes tube side. We've already gone through that. You don't want to go to the 4 and 6 pass type exchangers. All those are channel covers really, but keep it simple, sweetheart. KISS, K-I-S-S, keep it simple. Standardized, all your cleaning methods are the same. Everybody knows how to clean. And voila, everybody likes you again. This ain't working out, is it? I'll tell you. Things that I have to put up with. Or, excuse me, that you have to put up with. What's this say? Okay, there we go. Assuming higher fouling rates, don't. First off, you don't know what the fouling is going to be. You don't have a clue. But if you assume higher fouling rates, it's a self-fulfilling prophecy because you will get higher fouling rates, right? Larger units lead to lower velocities, lead to higher fouling. Good idea to monitor fouling data will show when you need to clean. Clean all exchangers at the same time, one shutdown. Don't wait until it breaks. Don't wait until it breaks. There's two things you have here. You have, if it ain't broken, don't fix it. Now that's a fairly good statement. There's nothing wrong with that. Then you have the other one, don't wait until it breaks. That's another one, preventive maintenance. They're contradictory. Both of them are quite good statements, mind you. If it ain't broken, don't fix it. And don't wait to fix it. Don't wait until it breaks. And there's two good statements. They're both right. They're opposites, but they're both right. Life's a terrible thing. Then you die. Anyway, then we mentioned something about non-condensables. There's no answer up there. If it ain't broken, don't fix it. That's very good. Very good. Very important. When I was younger, about 15 years ago, I was watching this slide presentation, and I nearly fell out of my seat. I thought the speaker was a complete moron. And you run into a lot of speakers that could borderline on that. And the slide, it said preventive maintenance was an extraneous expense. Preventive maintenance was an extraneous expense. Oh, my goodness gracious. What a terrible, terrible thing to say. Holy tamale. God help us, huh? Anyway, he said we could save a lot of money if we do away with the maintenance people. Oh, God almighty. I think God has a special place for the stupid. I'm not sure. Does God have a special place for the stupid? Anyway, you probably don't realize it, but there's a lot of design methods out there, right? You probably think there's only one design method. And the other thing I think is that once you got the design completed, you think you're done, right? Is that the idea you guys got? Well, let me explain something to you. There's multiple design methods out there, and design is a continuous process. You do one design, oh, great. Then you do another, and then you do another design. And I'm talking about how the real world works here again. I'm not talking about how college works. You guys around here, one design, you think declare victory. One design, you go ahead and design it again, you go ahead and design it again, you go ahead and design it again. So, you're under continuous designing process. So it's not one design and stop. It's design after design after design after design. The other thing you guys think about is you're going to design your equipment, right? Actually, your assignment may also be to design your competitors' equipment as well. Okay? Figure out what your competitors' process is and see where their weaknesses are, where their advantages are. You might learn something. So 2 things you design, stuff for yourself and your competitors' design. And in the way of heat exchangers, there's really one method that sort of stands out, and it's the Bell-Delaware method. You got these other ones out there. So design is not one time and done. You are continuously in design mode. Kearns method, a design procedure based upon maximum flow area, shell side. Get a low heat transfer, low delta P. Similar, Kearns, but difficult. Bell-Delaware and Kearns method. Remember, Kern was 1950. Come on, give me a break. That's old. Old, but gorgeous, I'll tell you. There's nothing better than sitting down and reading Kern. I'll tell you. Can't get any better than that. You know how people like to sit down and watch basketball? I just like to sit down and read Kern, I'll tell you. It's about the same way, Got to get it right, lads. Got to get it right. Anyway, just teasing. Anyway, you wind up with a low pressure drop. Bell-Delaware takes into account shell side much better. Both of these design methods have similar tube side stuff. They're very similar. Tube side, as you would expect. Tube is easy. Shell side is more difficult. Uh-oh. Did I run out here? Look at that. I've come to the end of this presentation. So, that was course notes 1. And so I think I got 25 minutes. So this dash into course notes 2. Oh, that was course notes 3. Let's close that one off. Uh-oh. I'll tell you, computers. Where am I? I guess I got to go to NCAT. .edu. Got to go Blackboard. Blackboard. Give me the login, please. There we go. There you go. Now close your eyes. Close your eyes. Whew. Got them closed? Sorry. So let's see here. We were chit-chatting our way through e-transfer, summer 270. We were in 340 here, 343. Let's go to chemical engineering. Course materials. See, they have the same thing. 1, 2, 3. So let's start up with number 2 here. And look at this. All these old exams I give you. Fantastic. We may dash into Mills for a second or two. Mills is a fantastic book. It's also out there. So let's go into 2 here. See what happens to us. Ah, look at that. So, and actually you'd want a comparison between, say, 3 design methods, see which ones goes. You have, first off, ease of use. Simple is Kern's method. It didn't take me too long to learn Kern's method. Bell, Delaware, I had to sit down and read through that thing. And literally it took me about 3 weeks to get through, you know. While you guys were watching basketball games, I was going through Bell, Delaware. Okay, it's a matter of where your tastes lie, right? You got to recognize. This is very important right in here. Very conservative. You know what that means? That means very expensive. Conservative means over design. You're not taking very many. This one's not conservative. That's very good. I think Tinker, who knows what Tinker was, Anyway, you have a lot of no's here with Kern, ceiling strips, differential, 2. Here you got yeses. That's what you want to go with, yeses. Okay. Anyway, there's some yeses and nos, whatever. By the way, if you get into computer packages, right, you won't have a computer package for Kern. That's old stuff. If you run into doing shell and tube heat exchanger designs, you will, on a computer, you will be, whether you realize it or not, you will probably be doing the Bell, Delaware method. So, I don't know who Tinker is. I'm sure Tinker was a great guy. Best to run units, inlet at the top, exit at the bottom. The hydrostatic head is on your side. You got that? You know what that meant? Right? Nobody ever tells you that, but... laminar flow, transition flow, not high transport capabilities. You want to try to avoid these. Unfortunately, you can't. One stream is very small. Change flow regime splits the viscous heating first, maybe. See, in laminar flow, you have viscous fluids, so you need to get those hot as soon as possible, get them moving. Condensation under laminar flow, not a great idea, right? You want you don't want any film growth condensation. Anyway, stratification, not a good idea. 2, shell and tube heat exchanger, spec sheet, lots of things. Design suggestions, some heuristics here. Any resistance dominant, take steps to reduce it, right? You got that? Calculate differences exist between allowable and calculate pressure drops. You should use as much pressure drop as you can. If you're allowed 10 psi, then use 10 psi. Or try to get near as 10 psi as you can. The higher the pressure drop, the more energy you put into the system, and probably also the better heat transfer. Saving delta P is not necessary, not always necessary. Take steps to remove design uncertainties. Do fouling tests. Well, that may help. May help you. Take a kidney stone. A kidney stone is basically a stone that appears in the body that's essentially fouling. So I personally had kidney stones. It was a real, what they say, a real experience. You got a woman who's had given birth to children, childbirth, and then they had kidney stones. And their first response was, give me childbirth. Kidney stones is terrible. Anyway, so childbirth is quite painful. You realize that, of course. And it's amazing we're even here. You better be nice to your mom because she went through hell to get you out. Jesus. Tough stuff going through that small opening like that. Jeez, oh man. You can't believe somebody designed stuff like that. Anyway, just a joke. So I went ahead and had my kidney stone. It was a painful experience. He said it's worse than childbirth. Anyway, so I took my kidney stone and I looked at it and I was told it was oxalate. Okay? Oxalate, a chemical compound. Guess what the water is filled with around here? You go drink some water, you're going to be drinking dissolved oxalate. Where does that dissolved oxalate go to? Your kidney stones. Now, oxalate's almost in everything. You use black pepper on your eggs for the morning, or black pepper as a seasoning. Black pepper's filled with oxalate. Got it? So what I did is I switched from drinking water out of the fountain to distilled water. So I drink distilled water so I don't get oxalates. Now, when I had my kidney stones, this was about 15 years ago or 12 years ago, the doctor looked over at me and he says, you'll be back. And I looked up at him and I says, no, I'm not. I haven't drunk. I try to avoid drinking water out of the fountain. Try to always drink distilled water. Make my coffee with distilled water, except upstairs. So I haven't had a kidney stone since. I'm going to knock on wood. Okay. Kidney stones, that's just a terrible thing. Here, anyway. So you do fouling steps. Let's see, don't say pressure drop, fouling tests. You might want to filter the streams, filtering to get out the big things. Heat exchanger, can you imagine putting sand through the, say you had a slurry of sand and water. Can you imagine putting sand and water through a shell tube heat exchanger, putting on a shell side? You know what would happen with sand on the shell side? It would just fill up the shell side with sand and your heat exchanger would come tumbling down. Now you could possibly, I'm not recommending it, put slurries through pipes. Now that might be okay, but even that is tough. So, sand being an example of something that was fouling. Fluid losses should be high to minimize fouling. Of course, streams dirty, might filter the streams, got it? So we're looking for design options, right? You come up with a good design option, you might save yourself an awful lot of trouble. However, by saving yourself an awful lot of trouble, you may also actually be putting yourself out of the business. So you got to do a little balancing act here. Upper management don't keep you around just to pay you. Upper management wants something out of you. So anytime when you have a significant problem, you don't want to solve it too quickly, because upper management thinks that it's easy then. You want to make sure you sort of draw it out more. Let the bosses get a feeling for how difficult you're having and how much they should consider how valuable you are. Because as soon as they don't know you're valuable, they're going to get rid of you. I'll tell you. You know, of course, the purpose of engineers is to get rid of the operators. It'll minimize the operators. And the business people, their purpose is to get rid of the engineers. I'm telling you the truth here. When I lie to you, what do I care? You know, I am too old to give a damn. When I was young, I didn't give one either. Anyway, so you're looking for velocities around 6 feet a second, 8 feet a second. Now, if you're dealing with vapors, 250 feet a second isn't too. The vapors, 20 is pretty low. 100, 200 feet a second. Fouling factors are assumed. The unit will not run clean. Got that? If you assume high fouling factors, you will have high fouling factors. Most designs are plus or minus 30%. Where this 23, I don't get came from. If you increase areas increased by 10%, nah, you don't want to do that. Excessive fouling factors may block tubes. You need to add standard operating conditions, add area to handle situation. Anyway, adding area considerations. High fouling, you want to use a spiral heat exchanger. We haven't talked about those, but that's fine. We're going to talk about them later. You might run into situations requiring special alloys or non-ferrous materials. You might try a plate heat exchanger. However, I wouldn't use a plate heat exchanger, and I'll tell you why later. Vibration analysis should be performed, stress analysis as well. Now, this is a really sexy question. Which fluids, which side, right? If I have corrosive fluids, tube side. Fouling fluids, tube side. High pressure, tube side, right? Bam, 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 bam. In here, you have less area to corrode, less corrosion rates. Wall thickness can be added to account for corrosion. You might use bimetallic tubes. Bimetallic tubes, they have a metal on the inside and different metal on the outside. What you do is you put one tube of metal inside the other tube of metal, load it up with dynamite, and explode it all the way down the length of the tube. And lo and behold, you metallurgically bind or metallurgically merge the two metals together, and you have a bimetallic tube with no surface there, right? That's great stuff. The company that does this, I think it's in Colorado, and they do their work in old caves or old gold mines up there, old mines. And their symbol on the New York Stock Exchange, it's on the NASDAQ. Their symbol is they're called BOOM, B-O-O-M, a fitting description for a bimetallic tube manufacturer. Fantastic, isn't that great? I'll tell you. High temperature fluid, tube side, there you go. Where is that up here? Tube side, avoid high temperature shells, avoid insulating shell. By the way, the reason why you insulate a shell is for safety reasons, so people won't burn themselves. We've got to realize that there's no such thing as an energy crisis anymore. I hope you realize this. We have lots and lots of energy, and what's really funny about this energy is it's cheap. So enjoy. Your whole life is going to be a wonderful life in comparison to what it would have been if we had 10 years ago, the conditions of 10 years ago. This fracking has changed your life significantly, positively changed your life for the better. And you should be very happy for that. And you should be more respectful for the hydrocarbon industry. God, you got those Kinkos out there running around amok. Everything wants to be a windmill or a solar panel. Those things are, let me tell you something. You poke a hole in the ground, you get natural gas. Best thing since sliced bread, I'll tell you. And the next time you try a solar panel car, notice how primitive it is, right? Oh, you're going to go electric. Going to go electric. The electricity came from power plants burning natural gas, or that terrible, terrible substance called coal. I'll tell you, that coal is so dirty. I'll tell you what, I saw on the news the other day that the Greenies in Boston, it was in the Boston Globe this week, the Greenies want to have you turn off your air conditioning in the summertime. So I highly recommend Greenies, I'll tell you, they're wonderful people. They're trying to save the planet. They're going to try to save the planet at your expense. Oh, God almighty. So, first point, no energy crisis. Second, energy's cheap. You realize that you're really, really lucky that gasoline only costs $2 or $3 a gallon. You could be in Europe, where you got them governments over there charging $8 a liter. Oh, geez, oh, man. And then they're taking the money and wasting it. Sorry, this is an energy course in part. It's about heat transfer, heat being energy. Anyway, let's continue on. Allowable stress. By the way, this is recorded. Remember that. Gases with dust, tube side, easier cleaning. Shell side, anything bad news goes tube side. You get that? You don't want anything in the shell. Shell is a first-class pain in the neck because it's got a really bad flow geometry. Got lots of nooks and crannies. Anyway, low pressure shell side, less leakage to the environment. There you go. So these are design considerations, which fluid, which side. Different flow rates, pressure drops, not clear. So like I said, you do multiple designs. You vary the flow rates, you vary the pressure drop. You put one fluid shell side, the other fluid shell side. You have small diameter shells, long tubes, large diameter shells, short tubes. So you go through all kinds of iterations. Again, these things cost $1 million. Your salary is what, 80K, 90K? 10 years you'll be able to pay for that heat exchanger with your salary, so maybe. Ah, there we go. The plate and spiral heat exchangers. Fantastic stuff. Again, we're not talking about phase changes. We're going to, in the next couple, a lot of the slides we'll be talking about plate and the spiral, right? Anyway, the shell and tube, the old workhorse. You can always get a shell and tube. But shell and tube are not necessarily suitable for everything. Right, processes which require low holdup. Oh, good heavens, what's holdup? Well, holdup is the amount of material that's held in the vessel. It's held up in the vessel. It's might be referred to as the working volume or the volume of material. So if you have processes which require a low holdup, your shell and tube might not be a good idea. And what processes might that be? Well, you consider the fact that orange juice, you're going to evaporate water or heat orange juice up to evaporate off the water. But orange juice tends to be sensitive to metal. You can put orange juice in a metal cup and you will have a metal taste to the orange juice. Metal ain't a great idea with orange juice. So you want to have as little exposure as possible, right? So you don't want to heat up orange juice or you don't want to have an evaporator with a shell and tube. Fast transfer required. This would be for pasteurization of milk. Instead of orange juice, just move on to milk. You want them homogenized very quickly. So suspended solids, well, if I was cooling down strawberry jam and the strawberries were big hunks of strawberries in the jam, it'd be hard to put a strawberry down a tube. And it would tend to be very cloggy. So then I might switch to a spiral heat exchanger. The other problem with shell and tubes is they're a lot of metal. A lot of metal, they cost a lot. Spiral and the plate heat exchanger, the original idea was over a century old. Like I was telling you, old is good. Okay, you got that? Old is good. And there you go. That's the first plate heat exchanger there. Let's see if I can. There you go. So you have the plates, you have cover, your front end, back end, movable covers, got a carrying bar, and basically these things are screwed together. These are screw points here. You have the inlet and the exit, inlet and exit. The flow rates have to be approximately the same there. The compression bar fits right in here and right in here. So the flow might come in up here, flow down this plate, and exit down here. Flow would come, this one might come up and exit over in there. So there you have it. Plate heat exchanger. You have plates, that's the heat transfer area there. They're corrugated, where they have a pattern. That's to create turbulence. They're also gasketed. They're made of gaskets right there. I personally would not buy one of these things, save my life. If I had one, I have no respect for this heat exchanger. If you never have to open it, never have to clean it, it's wonderful. Go ahead and buy it. If you're going to have to clean it once every 10 years, go ahead and buy it. It'd be great. But if you got to clean your heat exchanger every 6 months, it's a dangerous purchase. Now tell me, wise guys, why is it a dangerous purchase? What is the problem here? Why does old Tat here, old Tat, useless old Tat with his teeth falling out, telling you this is a ridiculous purchase? And for that, I'm going to leave that as a test question for you guys. By the way, since you've lasted this long, which is 2 hours worth, basically we got 5 more minutes. That's 120 minutes. The lectures are usually 50 minutes, which means that I've already lectured, I should be lecturing 100 minutes, whereas, well, wait a minute, I got to redo these calculations. How many minutes I have to spend. I got to make sure that the minutes I spend with you all are the same as the minutes that are spent with you in a regular semester. Anyway, so I got about 4 more minutes to go. The reason why these are taped lectures is primarily because I think the course begins on the 29th of June, and then that's a Thursday. Then Friday we have a day off, and then following Monday you come back, we have a lecture there. Then we have the 4th of July, and then you come back Wednesday after the 4th of July, the 5th of July. So my figuring is, number one, you don't like to go to school. That's the first thing. Secondly, you don't want to be around for a single day. And third, you don't want to be around a single day before a holiday. So this is why I'm taping these things, to send them out. So you don't have to show up for class on the 29th, and you don't have to show up in the class on June 3rd. You got it? However, you do have to watch these lectures, right? And so with that, and the point of the matter, why would I never buy a plate and frame or a frame heat exchanger or a plate heat exchanger? Sometimes it's called plate heat exchanger, right? I'll leave that up to you, and with that, I'm going to stop. And any questions, you can email me if you like. I may or may not respond, but you all have a good holiday. Be safe. Don't get yourself in bad straits come 4th of July. When you set off them damn firecrackers, get your fingers out of the way. The eyes, fingers, whatnot. You want to light it and run. Light them and run. Or light them from a distance. Anyway, have a good day. And I'll stop the recording now. Oh. Okay. Yep. Sounds like a great idea.